let's suppose I have two vectors. So I'm working from a point. I've got two vectors. I've got a vector S that's in the direction of my source, and a vector N that's in the direction of the normal of the surface. All right? Well, those vectors are whatever they are. Their unit vectors are sort of small s, small n. So remember, I can project any vector up onto the PQ plane, and that's what this is. This is at the z equal 1 PQ plane. So I've got a PQ for the normal of the surface, and I've got like P sub s, Q sub s for the vector that is in the direction of the light source. So when I write that, I get the following, right? Remember we said that our unit vector n is just PQ1 divided by the magnitude of P squared plus Q squared plus 1 square root of. And likewise, the unit vector in the direction of the source is just PSQS1 divided by its magnitude. All right? So far, so good. So we have an algebraic representation of both of those normals. So let's suppose for a moment we have a Lambertian surface. Then the only thing that determines, in terms of the geometry here, the amount of brightness that we see is just this angle I, which is kind of lost in this mess here. But there it is. It's the angle between those two vectors. And what I need to know, of course, is the cosine of that angle, right? That's the Lambertian surface equation. Well, given all of this algebra, we can represent that cosine as follows, right? The cosine of that angle is just the dot product of those two unit normals. So it's the dot product of n, dot product of s, which is the dot product of these quantities, which is written right there. Okay? So that is the representation in PQ space of what that cosine of that angle is.